This video is going to be about graphing logarithmic functions. But before we do that, let's quickly just review logs. So for instance, if we are to find log base 2 of 8, and we were asked to evaluate this, let's remember what we're looking for here. What we're trying to determine is what is the exponent of this base 2 that would give us an 8. So 2 to the what power equals 8, or another way of writing that out, what we're trying to determine is 2 to the x equals 8. And we know that x is going to equal 3, because 2 to the third equals 8. When we talk about graphing a function, the exponent that we're determining is going to be our y value. And then what it equals when we use that exponent is going to be the x value. So that's just some things to consider. So I just wanted to review how that works when we are evaluating a log. Just another one, for example, if we were finding the log base 3 of 27. Again, 3 to the what power equals 27. That's another one actually where the answer is x equals 3. Or just one more real quick. If we had a log of base 1/2, log base 1/2 of 4. So to work this one out, again, it's 1/2 to the x power equals 4. And x is actually going to equal -2. Because 1/2 to the -2 is the same as 1 over 1/2 squared, which is 1 over 1/4, and 1 divided by 1/4 is 4. All right, so just a quick review there. Now, so as we begin to graph, let's first of all think about the parent function. Now, this should say f of x equals log of x. Okay, that's the parent function of the logarithmic function, and I want to compare the log function with the exponential function. So remember, when you don't see the log base power of x, it's a 10, so log 10 of x, okay? And just think about it, 10 to the what power equals, the x. So if we did 10 to the 0 power, we would get 1. Or 10 to the 1 power, we would get 10. Well, when we do 10 to the 0 and equals 1, then our x value is the 1 and the y value is the 0. 10 to the 1 power is 10, but the 1 power is the y value, and then what it equals is the x value. So we have a 1, 0, 0, 10, so we plot 1, 0. It's our x-intercept. We go all the way out here to 10, 1, and you can see this is what the function looks like of log x. Well, a logarithmic function is the inverse of an exponential function. So again, if we have log 10x, the exponential function is 10 to the x. So when we do 10 to the 0, we get 1, and we do 10 to the 1, we get 10, and we already established that. But here, the exponent would be the input value, or the x. So we have 0, 1, and 10 to the 1 is 10. So the exponent is the x value, and what it equals is the y value. So we have our inverses. Over here, we have an x of 1 and a y of 0, and then they switch. Over here, the x is 0 and the y is 1. Those are inverses of each other. They're actually a reflection of each other across this line that's called y equals x, this diagonal here. So it reflects across that y equals x, okay? Now let's take a look at some examples, okay? Looking at this very first one, we have log base 2 of x. So the first thing I'm going to consider is just the exponential function. So if I take that 2 and I do 2 to the -2 power, I get 0.25. 2 to the -1 is 0.5. 2 to the 0 is 1. 2 to the 1 power is 2. And 2 squared is 4. Well, again, when we look at it in terms of graphing, the 0.25 that we got is actually the x value, and the exponent -2 is the y value. So I've written down the x and y values. So we have 0.5, -1, 1, 0, 2, 1, and 4, 2. Okay, and that becomes the table that we would graph for the points that are part of that function. Now, I want you to realize, and this is important when you have a logarithmic function, there's no exponent that you would raise the base to that's going to give you a 0, because 2 to the 0 is 1, and then 2 to the negative 1 gives you a fraction of 1/2 and 1/4, and we're getting closer and closer to 0, but you're never going to get 0. So with this function, that's the parent function, we do not have any shift or anything with the x plus or minus. It's just log 2 of x. We're never going to get 0 here. So that becomes what's called our vertical asymptote, okay? When x is equal to 0. Therefore, our domain is going to be all the values for x that are greater than 0. Your range is going to be all real numbers because it will continue to infinity, positive infinity and negative infinity on the range, okay? And then as our y value, our f of x is approaching positive infinity, the x value is also approaching infinity. But as the y value or the f of x, the function is approaching negative infinity, you can see that the domain or the x values are approaching 0. And then, of course, the x-intercept is here is at 1, 0. That's because anything to the 0 power is 1. So 1, 0. And then, of course, the asymptote that we discussed, okay? Now, you can see here the rest of the notes that you can take a look at are here at number 2. I'm going to move on to number 3. So in number 3, let's just zoom in here. Let's just look at the table first. Okay, so we have this function f of x equals log 4 of x minus 1. So the difference here inside this parentheses with x, we have a minus 1. This is going to affect our vertical asymptote. Think about it. The vertical asymptote is when this value cannot equal 0. Well, for x minus 1 to equal 0, that means we would be plugging in a 1. So it's kind of the opposite of minus 1. That 1 is going to become our vertical asymptote. But let's look at where the table comes from. Again, I'm just going to take this log base 4, this 4, and I'm going to raise it to some exponents. So 4 to the negative 2 is 0.06. 4 to the negative 1 is 1/4. 4 to the 0 is 1, and 4 to the 1 is 4, and 4 squared is 16. So I'm going to write these down as x, y's. Again, the x of 0.06 has a y of negative 2. And the 0.25 and negative 1 and so on. 1, 0, 4, 1, 16, 2. But because we have this x minus 1, remember with a parentheses inside the x, it shifts the graph right or left, and it's always in the opposite direction that you would think. So a minus 1 actually shifts it to the right one. So for all of these x values that we got, we're actually going to add 1 to them. So 0.06 becomes 1.06. A quarter, or 0.25 becomes 1.25. And so on. 1 plus 1 is 2, 4 plus 1 is 5, 16 plus 1 is 17. The y values do not change because there's not any plus or minus out here. So this table actually represents the log base 4 of x minus 1. Okay, and then let me let you take a look at the graph here. So again, we talked about the asymptote then shifted over here to 1, and it's not just 1, it's x equals 1 because this is a vertical asymptote where x is 1, okay? Therefore, your domain is x greater than 1. Your range didn't really change. It's all real numbers, okay? And as the y approached positive infinity, the x also approached positive infinity. But as the y approached negative infinity, the x is approaching 1, our asymptote, okay? Now let's zoom in on another one and take a look. So let's take a look at number 5. This has a lot going on here. This says f of x is equal to log base 1/2 of x plus 9 plus 4, okay? So we have a horizontal shift here with the x to the left 9, and we have a vertical shift plus 4 on the y value. But first of all, in order to graph this, now we use our calculator, as well to graph these functions, but I just want you to understand where they're coming from. So we take this log base 1/2 and we consider some exponents. So 1/2 to the negative 2. Well, again, that's 1 over 1/4. but 1 divided by 1/4 is 4. That's where that 4 comes from. 1/2 to the negative 1 is 2, because it's 1 over 1/2. 1 divided by 1/2 is 2. 1/2 to the 0 is 1. 1/2 to the 1 is a half, 0.5. And 1/2 squared is a quarter, 0.25. So I would write those down as a table: 4, -2, 2, -1, 1, 0, 0.51, 0.252, okay? And that's my table, but that table just represents log base 1/2 of x. Well, now over here in this table, I'm going to consider the fact that we're going to have to subtract 9 because we're shifting to the left 9 units on the x-axis. So for all of these x values, I am subtracting 9. And then here, the plus 4, that's going to add 4 to the y values of that apparent function, or of log 1/2 x. So this x value of 4, I'm going to subtract 9. 4 minus 9 is -5. The -2, I'm going to add 4. -2 plus 4 is 2. And then we go to the next point. We have an x at 2, but we're going to subtract 9. 2 minus 9, -7. -1 plus 4 on the y value, we add 4 to the -1, we get 3. The next point is 1, 0. But when we shift to the left 9, 1 minus 9 is -8, and then 0 plus 4 is 4. And then, of course, we got a half, okay, for our x and a 1 for our y. When we subtract 9 from 1/2, we get -8.5. And then when we add 1 plus 4, we get 5. And then 0.25 is our x. When we subtract 9 from that, we get -8.75. And then 2 plus 4 is 6. So you can see here we are approaching -9. That's because our vertical asymptote is -9. It's whatever we plug inside this parentheses to make a 0. So anytime you have a number added or subtracted to the x inside the parentheses, the vertical asymptote is going to be the opposite of that. So -9 is our vertical asymptote, and you could see it here or you could see it on your graph. Let me go ahead and zoom in on this part. All right, so again, we can tell the vertical asymptote right away without graphing, because we could simply look at this x plus 9, and we know the vertical asymptote is x equals -9. All right, therefore your domain is all the values of x that are greater than -9. Your range is all real numbers. And then your end behavior, as the function is approaching positive infinity, which is this way, as it's approaching positive infinity on the y-axis, the x is approaching -9, the asymptote. And as the function is approaching negative infinity, that's this direction here, you can see that the x values are approaching positive infinity. We have a x-intercept of 7, 0. You can see that on your table in your calculator. And then again, the asymptote is x equals 9, okay? So that's all that I'm going to show in this video, but you do have the rest of these notes to look at.